roles because I will be moving to this University of Sherbrooke, thank you, very soon in September. And in this talk, I want to talk about how orthology prediction can be difficult when you have divergence after duplication. So that's a problem. We have some algorithmic solutions that I'll briefly talk about, and I will talk about some nice experiments that we did. So let's start with a definition, like any good talk should. Two genes are orthologs if they descend from an ancestral gene that has undergone speciation, and if they result from duplication, they are paralogs. So really, orthology, paralogy is an evolutionary concept defined by a gene tree, and speciation events, duplication events. Okay, so here, A and B1, these two genes would be orthologs, because if you go back to the lowest common ancestor, the LCA, it's a speciation. And B1C2 are paralogs because the LCA is a duplication. Okay, so that's orthology, paralogy, and we care about these for two essential reasons. One is that orthologs and paralogs can be useful to reconstruct gene trees and species trees. Another reason is that people use orthologous gene to predict gene functionality. And this is mainly due to this orthologs conjecture that says that orthologs tend to perform similar functions and share similar DNA sequences, and paralogs tend to diverge. And the essential reasoning behind this conjecture is illustrated here. So let's say these are genes. You have an ancestral gene on top, and at some point it underwent duplication, creating two copies. And if this ancestral gene performs some function X that was important for the organism, well, now you have two copies. One of the two copies still has to do this X. Here is the left one, but the other copy does not have to do it anymore, so it's free to evolve and diverge however it wants and maybe become some other gene. So that's the basic reasoning behind this conjecture, that speciation preserves function, duplication introduces divergence. Okay, so to predict orthologs, we have two main categories of methods. We have these similarity-based methods that assume that DNA similarity implies orthology. So to infer orthologs, we build a similarity graph where vertices are genes and the edges are weighted by some similarity score. And what we do is we run our favorite clustering algorithm on this graph, and we get these orthologous groups. So that's similarity-based methods. We also have these phylogeny-based methods, which build a gene tree and identify speciation and duplication events on the gene tree. For instance, using reconciliation with a species tree. So when you do that, you have a labeling of the gene tree with speciations and duplications, and once you have that, you have all the orthologs, all the paralogs in the family. Right, so many methods fall into these two categories to predict orthologs. Here are some of them. I won't go into more details. I want to talk about what happens when you have this divergence after duplication. Because when you have duplication, you might get this asymmetric rate of evolution between the two copies. There's this standard model that says that one copy is going to keep the same rate and the other requires accelerated rate, like this picture that I had before. And actually, this is not the only possible situation. This is a table of the models, the duplication models that appear in the literature from this nice Nature Reviews genetics paper. And when you see an alpha beta, it means that you have this asymmetric rate of evolution. So it happens in neo-functionalization, modified duplication, adaptive radiation model. You might have something else. For instance, when you have some functionalization, you have both copies that start diverging or evolving together at a new rate. But really, my point is, okay, asymmetric rates of evolution does not always occur, but it does happen. And the whole question in this paper is, well, when it does, how well do orthology prediction methods fare? Okay? And I want to illustrate the problem with this very simple example. So this is a gene tree with the ABC genes, and suppose this is really what happens. You have this speciation on top and this duplication, which introduces just some crazy divergence, accelerated rate of mutations. If you have this tree and you build the orthology graph, this is what you get. Here, vertices are genes, and edge means orthologs, and non-edge means paralogs. And AB are orthologs, AC are orthologs because LCA speciation, BC paralogs. But in terms of similarity, what you might expect if you have this scenario is that, well, AB are going to be similar because you don't have some significant divergence on the AB path, but AC and BC will not be similar because of this wiggly edges that represents divergence. So when you build a similarity graph, this is what you would expect. And this is what you would expect these similarity-based methods to predict. And, well, they will miss this AC orthology because AC is a pair of non-similar divergent orthologs. Okay? Well, phylogeny-based methods now, they will find all the orthologs. If we're lucky enough to reconstruct the correct species gene tree and predict the speciation and duplication events correctly, if we have all that, we will find all orthologs. But there's still another problem here because, well, we have these similar orthologs and non-similar orthologs, and from what I've read in the literature is that people don't always care about all the orthologs. Okay, the AB orthologs are different from the AC orthologs because AC might not even share the same functionality due to this duplication and new functionalization event. So which orthologs do we really care about? Is it all orthologs, the similar orthologs, functional orthologs? Well, so in this work, what we wanted to do is just everything. We want to find all orthologs, even in the presence of this divergence after duplication. But we also want to distinguish between similar orthologs and non-similar orthologs. And we call them primary and secondary orthologs. And if you've been through some literature, well, you will find that primary orthologs are potential isoorthologs and potential equivalogs, which are essentially orthologs that share the same function. Okay, these have names, but yeah, okay. So this is the problem we are studying here. So let's talk about our algorithmic framework. We developed this DAD model. DAD stands for Divergence After Duplication. So we took it a bit to the extreme, and we just assumed that every duplication introduces this asymmetric rate of evolution. Okay, not everybody agrees with that. I don't, but just to you can think of it as a thought experiment. What happens if this is always the case, that every duplication has this wiggly edge? In this setting, we call two genes the primary orthologs if they're orthologs, and there's no wiggly divergent edge on their path in the tree. And the secondary orthologs are all the other orthologs. So in this example, the primary orthologs would be those related by an edge here. For instance, BE are primary orthologs because the BE path does not come across a wiggly edge. But BF are not primary orthologs because you do have this divergent edge on their path, right? And these would be the secondary orthologs, okay, that we would add to these primary orthologs. And now B and F are orthologs in this setting. Okay, what's convenient about this model is that it becomes very easy to characterize primary orthologs. Then under this model, primary orthology is an equivalent relation, an equivalence relation. That's an easy exercise once you've set up all the definitions. But that means that primary orthologs are just collection of disjoint cliques. So that's not very new, but as a corollary, it shows that what similarity-based methods have been doing, those that find one-to-one orthologs, actually find these primary orthologs. And just this basic property motivated our whole framework. We called it the HyPPO framework for hybrid prediction of paralogs and orthologs. It's hybrid because we use ideas from similarity-based methods and phylogeny-based methods. So what we do is this. We actually have a schematic representation. We just first assume that we have a gene family, so we don't have all the genes from all the genomes. We have an homologous family. We take the gene sequences, build a similarity graph, cluster, find the cliques of primary orthologs in this similarity graph, and then from that, oh yeah, I should mention this. So step 2, we compute these cliques, and at step 3, we want to find these secondary orthologs, the orthologs between the cliques. The thing is, there is a whole body of literature about how to do this. If we're not careful, we may predict nonsensical orthologs, meaning that there's no gene tree that has these orthologs. And we need a species tree to validate this step. I won't go into the details of how that works. I invite you to read the paper, but in this framework, we use the cliques of primary orthologs to build a species tree. And now from the species tree, we may infer the intercluster orthologs. And well, these steps 2, 3, and 4, they define some nice algorithmic problems. I would love to go into the details of these problems. Unfortunately, I don't have the time. I'll just mention what they are about briefly. So step 2, that's clustering in a graph. This is not new. But here we use a cluster editing formulation. So we're given a graph and we want to edit a minimum number of edges to get a collection of cliques. This is a well-studied problem. Here we used an exact fixed parameter tractable algorithm for a few genes and a heuristic for more genes. So to my knowledge, this is the first time that we use an exact algorithm to cluster orthologous genes. And I think that helped in getting good accuracy. So yeah, cluster editing. For the species tree, here what we want to do is we want to just use this information from step 2. We have cliques of orthologs, pairwise orthologs, and we want to use that to reconstruct a species tree. And the problem here is to find a species tree that agrees the most with the clusters that we have. I don't have time to define what agrees means, but that's a new algorithmic problem. I don't know if it's NP-hard. We just use a dynamic programming heuristic for this problem. So look at the paper if you like these types of algorithms. And we also have this intercluster orthology problem, where here we want to find the maximum weight intercluster relationships that agree with our species tree. Again, I will not go into the details, but that's the last step that we do. Okay? So let me talk about experimental results. So we implemented this whole pipeline, and we performed experiments on simulated datasets and empirical real datasets. For the simulations, we use SymPhy in conjunction with Indelible. So SymPhy or SymPhy, I'm not sure, SymPhy. SymPhy can simulate species trees and gene trees with duplications, losses, horizontal gene transfer, ILS. Here we just use duplications and losses. And so we generated species tree with 10 gene families each. And we had these 4 data sets, which each isolate some parameter, including duplication rates, loss rates, substitution rates across the trees. Okay. And we also simulated divergence after duplication, because Indelible, which simulates gene sequence evolution on a tree, does not do that. So we had to force these wiggly edges, if you will. So what we did is we took each gene tree and generated another tree by choosing one divergent edge for each duplication. Each duplication, and multiplying the length of the edge by 2, which simulates an accelerated rate of evolution. And we actually did that also by multiplying edge length by 8 and by 50. So this gave rise to all these data sets. So for each set, 4 sets of parameters, we had 100 gene trees with unmultiplied edge length, with edge length multiplied by 2, 850. Okay, so these were the simulated data sets that we had. And we considered these methods our HyPPO pipeline. We tested HyPPO with the true species tree. So we simulated species tree, so we know which is true, just to assess how the quality of the species tree affects accuracy. We also tested this OMA GetHogs software, which is nice software, and it can also predict these primary orthologs as well as the secondary orthologs. So it was nice for us to have some basis of comparison. And we also tested with OrthoMCL because it's a standard method. Okay, so this is the accuracy on simulated data sets. Accuracy is number of correct relations over the total number of gene pairs. So HyPPO are the first 2 blue and orange bars. It just says that we're pretty good. We get good accuracy. This orange bar is HyPPO with the true known species tree. It's always better to have the true species tree than to predict one. That's one conclusion. yeah, I should mention that, so you have these data sets and we have numbers. These numbers represent the edge length multiplier that we applied. And what you can see is that for our framework, as divergence after duplication increases, our accuracy increases, which is the opposite for OMA, and OrthoMCL has the same effect as us. Okay, and one important point is that so you have these STD1, EV1, and so on, which are the gene trees that did not have this divergence after duplication, no multiplied edges, and we're accurate even if we do not have this divergence, which was an important factor for the reviewers. So we built this whole model with this idea of divergence after duplication, but we don't need it. It's still accurate. Okay, so this is accuracy. This is the quality of the primary orthologs, the cliques of orthologs. So we devised this cluster score in the paper. And again, we're doing pretty good. This just says that we are better at clustering the primary orthologs together. And these are the averages on simulations for accuracy, precision, recall, cluster scores. We're doing better in every situation except precision. OMA is a bit better. It means that it predicts less false positive orthologs. All right. For the real empirical data sets, we use Swiss tree, which is a gold standard manually curated gene tree database. We tested our pipeline on these 8 eukaryotes. And in these data sets, the orthologs and paralogs are known. We don't have the primary orthologs, and we did not evaluate that on real data sets. So briefly, how much time do I have left? Yeah, maybe 2 minutes? All right, perfect. Well, accuracy tells pretty much the same story. We're doing good. It's always better to have the species tree. We're doing very bad on these VATB and SCRC gene trees. We looked at it, and the main reason is that the orthologs we predict many paralogs due to some duplication on top of the gene trees that we infer, which makes many paralogs, and these data sets have mostly orthologs. So this inaccuracy is due to a misplaced duplication. So that happens. So that's accuracy, and these are the averages. Same story as before. We're pretty much accurate, a bit less precise, but we have better recall. All right, so let me conclude with some future work. What I'd like to do is to consider other types of post-duplication behavior. Okay, I do not really believe that duplication always introduces divergence after duplication. So I'd like to consider other models of duplication, okay, which will lead to a more fine-grained classification of orthologs, because I don't believe that all orthologs are the same. It does depend on what happened in their evolutionary path. So that's one thing I'd like to do. I'd like to make HyPPO more scalable, because for now it assumes that you have partitioned the genes into homologous families. So it works fine for gene families on 200, 400 genes. I'd like to scale it to millions of genes. And there's an algorithmic problem that is still open that I mentioned. It's how to reconstruct a species tree from orthology clusters. If you're interested in algorithmic problems, well, you're welcome to look at the paper, because it is the main bottleneck in our pipeline. Okay, on that note, I thank you for your attention.
Very interesting. It's great to see that debate about the ortholog conjecture is still ongoing. I had a question for you. So if you're assuming that there is divergence after duplication, why wouldn't you also want to allow for there to be divergence after speciation? So it has to happen at least on a couple genes anytime you have speciation. Otherwise, you wouldn't have speciation. We would just be one organism. So why not allow for that to happen?
Because it would make everything so difficult. No, but no. I get the point. So this idea is just based on the reasoning behind the orthologs conjecture that it says that speciation does not tend to introduce divergence, duplication does. Now, how would we support divergence in the presence of speciation? I don't know. I really don't know.
Well, I guess you have to also be careful about how you phrase the ortholog conjecture. I think that
Yes.
even people who are very militant about adhering to or defending the ortholog conjecture wouldn't say that paralogs that are 5 million years old would be less similar than orthologs that are 150 million years old. So you should always be careful when you phrase that, just in case maybe someone who isn't a militant defender of the ortholog conjecture might be in the room. I mean, you know, there has to be some divergence after speciation, right?
Yes,
Somewhere.
yes, the
At
point
least
is,
one gene has to diverge.
Yes, the whole point is,
Well, that would be a divergence, wouldn't it?
yes,
Yeah.
there is divergence. Maybe, okay.